No. What did I spell? Did I spell that right?
I think so.
Calorimetry. Calorimetry. Obviously, it's what's his root word?
Calorie.
Correct.
And what is a calorie again?
So it's going to be the process of measuring what?
Trading calories.
Well, yeah. Changing calories. Do you have a certain number of calories right now?
Yes.
Really?
Calories.
In a
I
scientific
had
sense,
some
that
this
makes
morning.
sense.
I mean, maybe in my stomach a little, but I had a couple eggs this morning. But right. Remember, this is another one of those words where we use two separate. There's a big C and there's a little c. You guys remember what the big C was for calorie?
That's the food one.
What's that?
The big C was the food.
Yes, yeah, big C calorie is the food unit. Little c and both of the calories, what are they? Units of what?
Energy.
Yeah, they're units of energy. Little c, this is the amount of energy required. You guys remember? To heat
Oh, 1 cubic meter.
1 cubic meter, that'd be a lot.
Centimeter.
Yep, 1 cc of water, 1 degree Celsius. I don't know if we defined the food calorie
I think we did.
similarly. No, I mean, I'm saying, do we define it similarly?
As far as being 1,000 of those?
Yeah.
I think so.
No.
Kilocalorie, the same as food calorie.
Yeah,
We equated those two.
food unit. This is the same as a kcal. And it's equal to, so henceforth, a kcal or kilocal means the big calorie, big C, equals 1,000 little c's. Does that make sense? Calorie in the food is 1,000 little cows. So a big calorie is equal to a kcal. A kcal being a kilocalorie. And so,
Which should make a little bit of sense. You generate body heat, and so for every kilocalorie, what is the amount of energy necessary to raise 1 kilogram of your mass?
the more you eat, the hotter you get. Yes, actually, if you think about very large people with a plethora of extra calories, we store those extra calories as fat, which is a very good insulator.
So your body doesn't automatically turn them into energy, it stores them for later.
Right.
When then it's never used.
Yeah, hopefully it is. Well, I mean, obviously some of it is very necessary.
Yeah.
If you didn't have any fat is not, it's an insulator, but what other purposes does it serve?
Smooth skin.
Great.
Right?
No, girls have higher fat content. That's why it's
Yeah, to a point. I think that wasn't quite what I was looking for. But, well, I mean, what other obvious, where is the plethora of your fat, AJ? Where's most of your fat located? Right now, think about your body.
Legs, stomach, not my
Be
legs.
specific. No.
My butt?
Yes. So why is it in your butt? Why did God design it so that our butt has a lot of fat? So we have a cushion when we sit. So when we sit, we don't go, that hurt. It's for protection.
I really bony butts.
That's the other purpose of fat, is for protection.
And flavor. I mean, think
Talk
about
about
meat that
that.
you eat.
I don't.
All I got was like.
I don't need humans.
No, I don't either.
But I was talking about as far as bodily purposes, protection. That's essentially the other. So it's definitely stored. But these two relate, they're not the same. So basically, it's a little disgusting to think about when you eat, because you know the average meal for you guys are probably 800 calories, but those are big calories. So basically, with that piece of chicken that you just ate, you could heat, 800 calories. That would mean it's 800,000 calories, which means that you could heat the almost a cubic meter of water by an entire degree C with that chicken that you just, the meal
So
before you
weird.
Or you could take the little tiny cubic centimeter, you could raise the snot on the temperature.
That's
With
so
800,000
weird.
degrees.
So yeah, they definitely have a relationship.
I could focus the calories in on what part of my body I want to eat. I can actually create fusion in my body if I eat enough calories. Nuclear fusion.
Yeah,
Gosh.
Just 10 million degrees.
you focus on.
Yeah.
Is there a limit on temperature, by the way? Degrees Celsius? We've talked about it.
The upper limit or lower limit?
Yeah, because we know there's a low limit.
What is that?
Zero.
Absolute zero.
Yeah. So
Negative.
that's negative 200, so we
3.15. Yeah, upper limit. What's the temperature of the sun?
Hot. I don't know.
I bet Mr. Yashik knows.
I do.
I have no idea.
At the core, it's roughly 15 million degrees Celsius.
Would you say that there's a limit on temperature? Probably.
No, I would say not, because lower massive stars have temperatures in the hundreds of millions.
Wow.
It's pretty boring.
Which makes sense. There should not be an upper limit. You can keep adding energy to something. It's going to make it do different and weird things, but you can keep adding energy. At some point, you can't take any more away, though.
So if calories are units of energy, it would make sense that calorimetry is, if you try to read it as calorie, you will mess it up. So you just sound it out. Calorimetry is the process of measuring.
Calorimetry.
What do you think it is? Process of measuring.
Energy.
Yeah?
Measuring what?
Energy expended, energy.
Expended. That is your, sorry.
Well,
Energy.
here's the problem with energy expended. Why Mr. Gotcha didn't like that is because energy cannot be.
No, that's not the reason I don't like it. But yeah, I mean that's true also. Energy can't be created or destroyed. But it's not always expended. Sometimes it's absorbed.
Correct.
So we want to have a word that covers both ways. Used.
No, because that definitely insinuates that energy can be used. It can be taken away. It can be
Take it out to the trash.
just a simple word we're looking for. I'm thinking
Back and forth. Back and forth.
Transfer?
Yeah.
Yeah.
Energy transfer. I like that.
Or I was just thinking transfer or change. So what do we use? I mean, if you look at Mr. Gottschalk's calorimeter on board, it's a pretty simple thing. What is the instrument that he's using to determine it?
A cylinder? Like that thing?
Oh, come on, guys. What is this?
Yeah, look at what he's drawing.
Thermometer.
Yeah, a thermometer.
Oh,
Yeah.
I see.
It's a thermometer.
Thermometer.
Well, when you say it like that, it makes perfect sense. Thermal. Oh, okay. It's a
Yeah.
meter, something to scale to measure thermometer or temperature. All right. Yeah. And generally, we're transferring energy from one substance to another. If I'm stirring it, it's going from. Technically, I suppose it's going from my hand to the stirrer to the substance. If we drop something in, like another substance, like that chunk of iron, now it's going to transfer between those two things. And so this is where those equations, or those equations we had come in handy. This one. Remember what all this stuff means?
Well, change in heat.
What's this?
Heat.
Yeah, heat.
Um,
Specific what?
heat
Yeah, heat capacity. Yeah, specific heat capacity. You're both partially right. All right, and what's the little p mean? Not capacity. What's the p stand for?
Pressure.
Yeah, constant pressure. And then change in T would be, yeah, change in temperature. All right, so, and this is where we get that one substance is going to lose and one substance is going to gain. So, let's drop that chunk of iron in.
Sue has a question.
Yeah, Sue?
After the calorimetry, the what of like?
The process of measuring energy transfer from
Okay,
one substance to another.
okay, that's it.
So, if I drop a chunk, I'm drunk, how many calories? No, okay.
Wow.
Hopefully there's light beer. Anyway, what kind of, if I drop a chunk of iron in, and say the iron is very hot,
Oh no, we talked about this before.
so what's going to happen?
What?
It's going to sizzle, it's going to drop in this hot substance is going to go in the water. It's like the dry ice. We drop something super cold in the water, what did it do to the water?
Made it boil.
Would
Made
Chilled the water.
It chilled the water, yeah, cooled it, right? So energy was transferred from the carbon dioxide to the water? No. How was energy transferred there?
The water to the
Carbon dioxide.
Yeah.
If it was.
Carbon dioxide heated up, the water cooled down because it gave, again, they share heat. It gave its energy very generously to the carbon dioxide so it could all equalize at the same temperature. So, one thing loses and one thing gains. Now, the problem with that is, let's say that something loses 4,000 joules of energy. That's negative, right?
Yeah.
Well, a negative can't equal a positive, okay? And this is what we were getting the other day that we ran out of time to explain, okay?
Wait, do you really say I lost a negative amount of blah?
No, you just say I lost 4,000 joules.
Exactly.
Yeah, but where does that negative go? We kind of put it before the temperature change, okay? Remember, changing temperature is
Oh,
Tf minus
that's
Ti.
negative also.
And so we distribute that negative, and we end up with negative Tf plus Ti, and then we just flip it. Okay? Oops, minus.
Yeah.
Okay? Does that make sense? So that's why we flip the temperature change here. So basically all we're doing is we're making the temperature change always positive. And that way we have positive joules and positive joules, and so we can equalize everything. Because again, the heat is equalizing. The temperature is equalizing. So on the loss side, just remember the change in temperature, change in T will always be positive in calorimetry.
Oh yeah, it's changing.
Okay, so you can think of it as the absolute value of the difference in temperature.
Which side will always be positive?
What'd you say?
Change in T.
Yeah. Now, obviously, I know that if I drop that chunk of hot iron in the water, I know the iron is going to lose energy, right? I know it's going to get cooler. So I'm going to have to remember, okay, the iron's on the loss side, so that positive change in T, I just have to remember to subtract that later on, okay? So it's just kind of remembering. We're not going to write any of, I mean, you don't need to worry about the negatives. What I would just say do is write it like this right off the bat. And over here, we would have MC Tf minus Ti. Okay, so now these will equalize. So there's an example in the book that we can use. Go to page 373. You have a 0.05 kilogram metal bolt heated to an unknown initial temperature. All right, so there's a bolt, and it's hot. We don't know how hot. In other words, we don't know it's Ti, right? It's dropped into a beaker containing 0.15 kilograms of water. at a temperature of, what was it, 21 initially? Yeah. And the water then raises temperature to 25. What will the temperature of the bolt be at that point? Also 25, right. So we can use this over here to find out the initial temperature. Now they give us a specific heat, and remember there's that chart on page 372 that says specific heat of certain substances. Here they're telling us it's a metal with a specific heat of 899 joules per kilogram degrees Celsius. So 899 joules, it doesn't match up with that chart, so it's probably some kind of alloy or some kind of mixture of metals, right? So you just plug what you know. And here's where you can just do change in T at first, and then do the TF minus TI later on, okay? Because the change in temperature, well, wait a second, is the change in temperature going to be the same between those two? In other words, can we just say, okay, the bolt was probably 29 degrees, right? Because if the water raised 4, then this dropped 4.
No,
No. Why not?
because the proportions aren't the same.
Not only the portion, so not only the mass, but also the specific heats are different, right? So it takes a different amount of energy. It takes less energy to heat or cool the bolt. So, you send them with each other. We know one's losing, we know one's gaining. Plug in what you know. What no? 0.05 kilograms, 899 joules per kilogram. I don't know that. But on this side, I do know change in T. 0.15, water 4186 joules per kilogram degrees Celsius. You will probably memorize that one because we use that one all the time. Just looking at the density of water is
1.
you failed. No,
I don't
1,000.
1,000.
Oh.
And then 4 degrees Celsius, so times 4. So that's it.
Oh, the
It is
1.29
1.
was
It's
the
1.
pressure.
It's 1 kilo. No, it's not. Because if you convert, then you have to do units too.
Yeah.
Deci something could be.
We often think of the water,
Or deca. I should
you know,
say.
frame of reference, we use it as 1.
Deca.
So anyway,
No, I wasn't. I was looking at that.
Oh.
so what's the temperature? Or not? Well, what's the change in temperature?
Figured it out. Um, 0.01.
0.01? Doesn't sound right.
If that's all you do.
No, I think you did something wrong in there.
Okay. 56.
56, yeah. Roughly 56. 55.875. I think you may have divided this by this instead of the other way around.
Yeah, that's
Wait, I really guessed 56.16.
You guessed that?
I guessed, not to 55.
Oh.
55.88.
Did you not? This is 9 out of 4. Did you use 9 there?
I didn't get that at all.
I got 55.8.
I didn't get that.
Okay, let's write the next step.
Oh.
Good. And then as we know from algebra roll, we divide by 44.95. All right, so if it changed 56 degrees, roughly, then what was the initial temperature of the metal? This is the easy part, guys. The bolt ended up at 25 degrees when it started.
Negative 31 inch.
Oh, wow. No, I guess it had to be hotter, didn't it?
Yeah.
That's where you got to remember what side we're on here, Okay, this is one that lost. Okay, the final was 25.
So 80?
Yeah, 81, right?
Well, yeah, 80.
Oops. So the initial temperature then is 81 degrees Celsius. Does that make sense? That we drop it until it's 81 degrees Celsius, it cools to 25 and only raises the water 4 degrees?
Yep.
Yeah, because again, we know that water takes an astounding amount of heat, of calories to change temperature. So there we go. That's all we got. What did you say?
Why do we know that?
Because water is more dense.
Water has
No,
high
it's not
specific
it.
heat.
Water has very, very high specific heat. That's why do you think it's necessary, by the way?
For our bodies, we insulated.
Beautiful. Not well.
Well, to not
I don't know if
get cold
insulated
too
is the
fast.
right term, but go on,
Yes.
elaborate.
Heat up or get too cold too quickly.
Correct. If you think about our body is what percent water?
About 70.
So-
70 or something like that percent of our mass is actually water. Well, part of the reason, I mean, and this is me kind of peering into God's brain when He created water, however many years ago, but if He had the brain, I don't know. But thinking about it, it makes sense because otherwise you'd walk outside in the cold, and if you didn't have a coat on, you'd be stupid. But either which way, you can walk out in the cold now and probably live for an hour, even if it's 0 degrees. Well, if the specific heat of water were lower, you would go outside and your body temperature would change so quick. If it were like the same specific heat as, I don't know, what's something lower, alcohol or.
Are you saying this is the reason that the water have high?
So if we were 70%
One of many reasons.
alcohol.
Yeah, one of many reasons, but yes. Whatever.
Think of you guys see the movie The Day After Tomorrow,
Yes.
where they like go outside and they
Yeah.
That's kind of how it would be
Yeah.
if the specific heat of water were not so high.
That would be so weird.
so the body
It would, well, the whole world would just change temperature so much more quickly. Like on Thursday, it's supposed to be 85 degrees.
Yes.
What is Wednesday? What's supposed to be 85 degrees? Here we are. What's supposed to be 85 degrees?
There.
The air is supposed to be 85 degrees, specifically the air in Chicago.
Yeah.
If the specific heat of water were not so high, because the air in Chicago were 85 degrees that day, all of a sudden you wouldn't be able to touch the because basically the ground, same thing. You're talking about a plethora of water in there. So the fact that water has a high specific heat plays into our
So-
day-to-day lives so much.
With if it was lower amount of specific heat, then it would be like it's 200 degrees today.
I would defer to Mr. Gottschalk on that one.
Say again.
No, I mean the sun wouldn't come any closer. I don't think it would affect
No,
our
it's-
maxes and mins of temperature, if that makes sense.
Okay.
But
You're saying if specific heat of water were less?
we're less, would we have higher temperatures?
I think I think we'd have higher highs and lower lows
But why?
because it wouldn't take as much energy to heat things up.
Oh, you're right,
Heat it
right.
higher.
Because of the direct heat of the sun. Yes. Yeah.
Just
Well, I don't know if it would
Even
get too
now,
hot.
like in the sun, it can be
That's
like 10 degrees difference than in the shade.
Yeah, that's true.
Yeah, and the sun doesn't heat the atmosphere. The sun heats the ground, and the ground heats the atmosphere. That's why the hottest time of day is not noon. The hottest sun should be at noon, right?
It's like
Mhm.
Yeah.
3 o'clock and
There's a delay there because the ground absorbs the infrared radiation from the sun,
Oh,
and then it
that's
re-emits it
interesting.
in a different infrared wavelength that then the atmosphere can absorb.
Mhm.
And so it warms up a little later.
Yeah, I remember being in Arizona and the difference in the degrees. Like, because we were by a pool and, like, it was in the sun and it was, like, 90 something, and all of a sudden it became in the shade because the sun moved and it was, like, 70.
Yeah, we used to go to
So
spring
weird.
training, baseball games in Arizona in spring every time, and you always wanted. It was hard because you wanted to be in the shade so you get sunburned, but if you're in the shade you were freezing,
Yeah.
and in the sun it was blistering. So you
Is
wanted
that
to be somewhere to
because-
go back and
wait.
forth. there's not
It's
much-
less humid there, right?
Right, and that's
Yeah.
why there's not all that water in the air, and so the specific heat of the air is less.
yeah.
So it,
When
And that's why
Sun effects
everybody
cool.
thinks of with the desert, you think of hot temperatures, but at the same time,
It's
the desert
really
gets
cold.
really cold at night
Mhm.
because basically the only heat source it doesn't sustain itself as well.
Yeah.
Which oftentimes we complain about in the summer. Oh, it's not the heat, it's the humidity that's killing us.
Yes.
Because in the nighttime, the heat is being sustained exactly through what Mr. Gatchett was saying. The fact that the air has more moisture, more water in it. So the air in itself is not going to change temperature as quickly because of the water in it. So.
And you will realize, actually, if you think about it, dew point, do you guys know what dew point is? Like the dew point tonight might be, it's supposed to be what, 60 today?
Is
The
that
dew
like
point tonight might be 45 or something.
the temperature when it like, yeah,
What is dew?
the water on the ground?
Yeah, let's use science term.
I don't know.
Starts with a C. Dew?
That's what start with the C.
Concentration.
Not concentration. What is
It's
the
a change
process?
of phase.
Yeah, what's that change of phase?
Oh, condensation.
Yeah. Remember how I'm looking at you through a bunch of water right now, water vapor?
Yeah.
It's invisible, it's just in the air. Well, that takes a certain amount of, I have to take a certain amount of energy away from that in order for it to condense into liquid, right? So if the temperature is getting down to 45 tonight, there will be no dew on the ground. If it does, then water will start condensing and there will be dew on the ground.
Weird.
And you'll always notice that the temperature never goes far below the dew point. Winter, summer, whatever it is, check the nightly low, and it will probably be pretty close to the dew point. It will never be below by more than a degree or two. Because if you think about it, the water is changing phase, right?
Yeah.
It's taking all that energy.
You guys know what we're talking about dew?
No.
Dew is the water that shows up in the morning. Like when I walk my dog every morning, I come in, my shoes are wet. It's the water that condenses itself onto the earth.
Even if it doesn't rain.
Right. Yeah. That's where
Okay.
frost comes from too.
How do you spell
So,
D-E-W.
D-
Like
D-
mountain
yeah.
dew. Mountain
So in
dew.
order for that water in the atmosphere to condense, what does it have to do? Is it endothermic or exothermic?
Excellent.
Exo, yeah, it's releasing heat. The water has less heat, so now it has to be a liquid. So where does the heat go?
Into the atmosphere.
The atmosphere. So the atmosphere can't cool anymore because the water releases all this heat.
Ice.
Okay? So check that out sometime. The dew point and the low temperature in the night should, if there's dew, the dew point and the low temperature will be about the same. Okay? Sometimes the temperature doesn't get low enough for dew, but it will never go much below the dew point. Anyway, what about changes of phase? What if, let's say that I am cooling steam. Let's say I have steam, water vapor at a temperature of, 200 degrees Celsius, and I'm cooling it to a liquid. Can I still use this? Oops, MC changing T, can I still use that? Does that still work? For a change of phase?
Because it could change the specific heat. Because ice is
Okay.
different than water.
Very true, they have different specific heats. But isn't there something else here? What's going on in here? Here's 100 degrees Celsius, so here's our heat of vaporization. Remember, temperature's not increasing here, but we are still adding heat, right? Or if we're going backwards, temperature's not decreasing, but we're still taking away heat. In order for the water to rearrange itself into a liquid and not steam anymore. So, can I use this if I'm changing phase? What's changing temperature? 0, right? Can I use that? Is it going to work? No, it's not going to work. So we have a different formula. Q can either equal this, but the amount of heat can also be mass times, what do you think that L stands for? It's a big L. Say again? Latent heat, right. Careful, because this is also a symbol for milliliters. That's not what we're talking about here. This is mass times latent heat. Latent heat of vaporization or latent heat of, what would this one be? What's that one called?
Melting.
No, there's a special word they use for the heat of blank. Think of chilling it. Think of chilling it, so we're going backwards, okay? You're freezing something. So because you're freezing it, the water is no longer free to move around. No one knows the term? Did you guys all read? You guys have read section 10.3 already, right?
Yeah.
Does it see what was in there?
It's forever.
What'd you say?
You got fusion?
Fusion, right, fusion.
Oh.
Not nuclear fusion, this is the fusion of just, well, it's the same process, we're fusing things together. We're fusing other water molecules together, so now they're attached to each other more rigidly. So that's heat of fusion. So it's going to take a certain amount of energy to cool that ice, or to cool that water down so it can freeze. So we can use this too. So look at page 381, or 380. We got 10 grams of water starting at 133 degrees Celsius. In other words, it's water vapor. And they're cooling it to a liquid at 53 degrees Celsius. So we're starting up here, right?
Yeah.
So it's not going to be this simple this time. Okay, we're going to have different stages of cooling. Okay? So what's the first stage? I start taking energy out of this, and what happens to it?
It becomes a liquid.
Not yet, because it's still way above that heat, or still above that temperature of 100 degrees C. What happens before? What has to happen before it can become liquid?
It starts bonding.
Well, yeah, but what happens before it can even start bonding? No.
The temperature decreases?
The temperature has to go down to 100, yeah, right. The temperature has to decrease. Okay, so we have one thing going on here. We have an MC change in T there. But then in here, temperature's not decreasing. You know, now it's 100 degrees C here, and it's 100 degrees C here. Difference is, here it's steam, and here it's going to be liquid. And this is all changing, okay. Lots of steam, little water, a little more water, a little less steam, a little more water, a little less steam, all water, no steam. You know, so slowly it's switching. But it's all staying the same temperature. So over here, we have a second phase, or a second stage where we use the phase change, the latent heat. And then we're going down to 53 degrees Celsius. So I have to be at this point right here before the temperature starts decreasing again, right? So now from here to here, I have a third stage where we have another temperature change. Okay? So there are three separate things that happen to make it lose energy. First of all, we have to take enough energy out to cool the temperature to 100. Then we have to take enough energy out to change the gas to a liquid. Then we have to take more energy out to make that 100 degrees C liquid cooler. Okay? So now we have different things going on. So look at that sample problem they give you. 10 grams of water cooled from steam at 133 to liquid at 53. So the first stage, MC change in T, our energy, this is going to be the first part of it, okay? We know the mass of the water, 10 grams, specific heat of steam this time, and the change in temperature is what for that first part?
33.
33, yeah, we're not going all the way down to 53 degrees yet, we're just going from 133 to 100. So specific heat of steam is what?
201.
Yeah,
No.
2000 or 2010. About half the water, right? Water is 4186. So that's stage one. Then we have stage two.
How does that work? Oh wait, I used the wrong one. See, never mind.
So this is going to give you just the amount of energy necessary to cool that amount of water down. Then the second stage, we take that same 10 grams and we multiply it by the latent heat. So this is how much energy it's going to take for the 100 degrees C steam to do what? To condense, exactly. So there's no change in temperature, which is why it's not shown there, because that would give us a 0 and screw everything up. So we have a latent heat of, now look how much that is. Latent heat of vaporization, 2 million, right?
Wait.
2.2 million. See that list down there?
What's the difference between vaporization and evaporation? We never talked about that.
Let's finish this problem first, then we'll do it.
Wait, where's that list?
Page 380. Sorry, did I not tell you to change pages before?
Yeah, sorry, just wait.
They just, I mean, they give it to you on 379, but they're just showing it to you on 380 again, so you don't have to flip pages.
Oh, I see.
Okay, so that now here, this is how to get it from steam to liquid. Now I have to cool that liquid down from 100 to 53. So I take my 0.10 again, water, specific heat this time, and 47 degrees. You add up all those things, Q1, Q2, Q3, that's how much total heat was lost by the water to go from 133 to 53. All right, so homework for tomorrow, page 374 and page 381. 10C and 10D.
And C and 10B? Oh,
Yeah.
D.
Try to do at least the first 4 of each section. Okay, I don't want you to get 10C done, not do anything in 10D. All right, so even if you don't get it all done, try to get at least 4 of each done.
Okay.
The first 4. It'd be best if you get it all done. That'll give you the best, obviously, practice at it. All right, let's go.
Yeah, what's up? Do I have stuff for you to do? You have a take home